All right. So the question reads that how much heat energy is required to convert 5 kilogram of 5 kilogram water of 5 kilogram of ice at 0 degrees Celsius into 5 kilogram of heat, steam at 100 degrees Celsius. Then we are asked to take, we are given the specific heat capacity of water to be 4,200. Then the specific latent heat of fusion of ice, 335 kilojoules per kilogram, and specific latent heat of vaporization of water, 2311 kilojoules per kilogram. In our last meeting, we looked at calculations involved in latent heat, change of states. Okay, calculations involved in change of states. And then we saw that the amount of heat energy to change state from liquid, solid to liquid, which is fusion, we got it as Q subscript fusion is given by the mass times specific latent heat of fusion. So M times LF, and LF is constant. Then specific latent heat of the quantity of heat energy that must be absorbed in order to change state from liquid to vapor, QV is equal to M times LV. All right. Now, when you look at this question, the question is such that 5 kilogram mass of ice at 0 degrees Celsius, and it is being converted to 5 kilogram mass of steam at 100 degrees Celsius. So when you look at the whole thing, we are changing states. We are expected to change states from ice. Okay, so from ice, it will change to liquid at 0 degrees Celsius before we heat the liquid at 100 degrees Celsius in order to change to steam also at 100 degrees Celsius. So when you go through it, you have 3 stages. You have amount of heat to change states. That is the first method, to change states from ice to liquid at 0 degrees Celsius. Then when the ice fuses or melts, okay, to liquid at 0 degrees Celsius, it must also absorb heat energy to raise its temperature from 0 to 100. So heat energy, the second stage will be heat energy to raise its temperature from 0 degrees Celsius to 100 degrees Celsius. So once we have water heated to 100 degrees Celsius, then at 100 degrees Celsius, don't forget that's the boiling point of water. So change of state would also start. So the heat energy, amount of heat energy also required to change states, from 100 degrees Celsius water, okay, to 100 degrees Celsius steam will be the next step. So when you look at the whole question, okay, it involves 3 different states or stages. Class, are you with me? Hello.
Yes.
Good. So you go through one stage at a time. So let's calculate for the amount of heat. You see, since the temperature of the ice is at 0, the moment ice gains external energy, it will start melting because we are starting from the melting point of ice. So the quantity of heat energy to do the fusion will be the mass times L of fusion. The mass is 500, 5.00 times, what is the specific latent of fusion of ice? This was given as 335 kilojoules. Okay, so 335, I will change the kilo to just joules. All right. And please calculate this for me. What is 3 times 335? 3 times
1675.
1675 times 10 to the power 3 joule. So this will be the quantity of heat energy to do the melting from ice to water. Then, so this is actually water at 0 degrees Celsius. Don't forget, I said that when change of state begins, okay, it occurs at a constant temperature. So ice will begin to melt at 0 degrees. So from 0 degrees upward, we have, when change of state is occurring, we have ice and water in equilibrium. The temperature will change when every ice has actually changed to water. So we'll begin with ice at 0 degrees Celsius, and then water melted also at 0 degrees Celsius. All right, so once we have water at 0 degrees Celsius, then the heat energy again to raise the temperature of water from 0 to 100. And this is about sensible heat. Okay, sensible heat. So Q, the second stage will be Q is equal to MC times delta T, which is the mass is 5, specific heat capacity of water 4,200 times the change in temperature, okay, from 0 to 100. So times 100. And this is already in joule because we have expressed the specific heat capacity in joules. Please, are we there? So put this together. Put this together for me. 5 times 42. Just give me 5 times 42.
That's 210.
2100 times 10 to the power 3 joules. Okay. Then after raising water to this temperature, don't forget 100 degrees Celsius is the boiling point of water. So change of state from liquid to vapor would also begin. So we calculate this amount of heat to do this for us. And that is vaporization. So mass times specific latent heat of vaporization. So 5 times, what is the specific latent heat of vaporization of ice? This were given as, this were given 2311.
2000
Yes.
kilojoules. Yes.
2311 kilojoules. Okay, times 10 to the power 3. Today you spare me. I'm just practicing the use of the smart board. So my handwriting, I don't even like it myself. Okay, so multiply 5 by 2311.
If you get 11,555.
11,000. Hold on.
555.
Oh, okay. Okay. 11,555. Yes, you have to be patient with me to master this thing. Okay, so this is times 10 to the power 3 joules. So the total energy Q total will be adding all of them. Okay, 1675 plus the next one 2,100 plus 11,555 all expressed in kilo. So put the numbers together for me. Au revoir.
Mr. Dear, please. I don't really understand the second part.
Okay. Au revoir. The point is that, you see, we have ice at a temperature of 0 degrees Celsius, isn't it?
Yes, please.
Now, once ice absorbs energy, what do you think will happen? When ice gains energy, what do you think will
It will melt.
It will melt. Why is it melting? Why is it melting? Can somebody help? It will melt because we are starting this at 0 degrees Celsius. And don't forget, 0 degrees Celsius is the melting point of ice, implying that when the temperature isn't at 0, we wouldn't begin with change of state. So when everything has turned to ice, we started with ice at 0, and we now have melted water at 0 degrees Celsius. Are you okay?
Yes, please.
So water at 0 degrees Celsius, when it gains extra energy, extra heat energy, its temperature must increase from 0 to 100. And this amount of heat is responsible for changing the temperature from 0 to 100. And that is sensible heat. The reason for which this scale is denoted as mass times specific heat capacity times the change in temperature. So that's the second step. Are you fine?
Okay, yes, please.
Then, once we have water whose temperature is raised from 0 to 100, do not also forget that 100 degrees Celsius is the boiling point of water. So at that temperature, what do you think will happen? What do you think will happen again?
The water will turn into steam.
Exactly, because we are at the boiling point. So water turning to steam is the third point. So it's about 3 steps. Okay, water turning to liquid at 0 degrees Celsius. Water, okay, with the temperature being raised to 100 degrees Celsius. Then water turning to ice at 100 degrees Celsius again. So the whole steps will involve 3. And that is the individual amount of heat energy required is what we've calculated. If we are looking for the total heat required to do that, that is the summation of what we have on the board. So please, can you put the total energy for me?
I had 15,000 330 kilojoules.
Exactly. This is the total energy, heat energy required to change water at 0 degrees Celsius to vapor at 100 degrees Celsius. Please, any question? Any question?
Yes.
Okay, I want to make slight changes. Priscilla, are you there?
Yes, sir.
Okay, I want to make slight changes. And the changes is that, please, this time is the same ice, but ice at -5 degrees Celsius. Change to water at 100 degrees Celsius. Okay, the same question, but we are looking at water at -5 degrees Celsius. Okay, to be changed to water at vapor at 100 degrees Celsius. What will be the total energy? Take the specific heat capacity of ice. Let me give you the specific heat capacity of ice. That is 2050. Take the specific heat capacity of ice to be 2050. So the total energy required to change ice at -5 degrees Celsius to vapor or steam at 100 degrees Celsius. Calculate the total energy required to do that. I'll be doing some drawing. So whilst you are working on it, I want to switch to the board to go through the drawing with you. Okay. So please use the time to do that while I'll also set my stuff up for me. We are back back to the Stone Age. Are we done? Hello, are we done? Class, can you hear me?
Yes, please.
Yes.
Okay. Are you through with the question? Hello, are we through? Hello, class. Can you hear me?
Yes, please.
All right. I'm asking if you are through with the question. Now, looking at the question I gave you, you see the difference here is we have ice at 0, ice at 0 degrees, ice at negative 5 degrees Celsius being changed to steam at 100 degrees Celsius. So the only addition to the question would be, you see, looking at the steps would be raising the temperature of ice from negative 5 to 0 plus the amount of heat energy that would melt the ice at 0. So MLF. Okay. So when every ice changes to water at 0, then the amount of heat energy that would raise the temperature of the water from 0 degrees Celsius to 100 degrees Celsius. Then the last would be the amount of heat energy that would change state from liquid at 100 to steam at 100 degrees Celsius. So the only addition is this part, because we have gone through latent heat of fusion 5 times 335 kilo. Then we went through this part where we had 5 times 4,200 times change in temperature of 100. Then plus 5 times, I think 2311 kilojoule. Okay, so we've done this 3 stages, stage 1, 2, 3. The only thing which will add to this question will be the mass of ice 5 times. Then I gave you the specific heat capacity of ice, 2050. Okay, times the change in temperature from negative 5 to 0. So 0 minus 5. So this is the only heat energy that would add up to whatever I've given to you. Class, are you okay? Are we okay? Hey, are you there? Class, are you there?
Yes, please.
Yes, sir.
Yes,
You are not talking. Are you okay with the explanation?
yes, please.
Yes, sir.
Okay. Then let me give another one to try so we continue with our work on cooling curve. The cooling curve is actually not difficult, but let's test understanding of this the last time. Okay. All right, let's treat the cooling curve. Then I upload the question rather after explaining this. So cooling and heating curve. Heating curve. In cooling curve, what we are actually doing is that we are plotting a graph of temperature against the quantity of energy used. Okay, so the cooling curve and heating curve is actually a graph of temperature on the vertical axis against energy on the horizontal axis. Temperature in degrees Celsius and energy in usually in kilojoules. Kilojoules because the energy involved can be huge. Okay, so when we plot the question we just solved, we are beginning with temperature of 0, then to the temperature, let's say 50, this is 50, then if we are taking 50-50 intervals, then that's 100 degrees Celsius. And in each stage, a certain amount of energy was used. So it can be 3, 4 stages. The first one was 3 stages. The second one was 4. So all that we are doing is that we are plotting a graph of energy use or temperature on the vertical against the energy on the horizontal. So this can be Q1, Q2, Q3. Let's use what we solved as an example. Okay, so 0 degrees Celsius ice turned to 100 degrees Celsius steam. All right, so what is the first energy involved? Q1. Q1 fusion, because the initial temperature of ice, okay, what's at this? Fusion mass 5 times latent heat of fusion of ice, 335 kilojoules. We put this together and had 1675 kilojoules. Please, is that correct? Is that the answer?
Yes, please.
Then Q2, after everything melted, okay, the temperature of water at 0 was raised to 100. So the quantity of energy used 5 times 4,200 times 100. And I think what did we obtain here? What answer did we obtain? 5 times 42. Okay, so I think this gave us 2100
Yes, please.
kilojoules. And then the third stage, latent heat of vaporization. So 5 times 2,311 kilojoules. And what is this? What is this product? 2311 by 5. This also gave us 11,555. Good. So if we are to, this is actually a heating curve. This one is a heating curve because ice at 0, okay, steam at 100. So if we are to plot a graph of temperature against energy at 0 degrees Celsius, change of state occurred. So this is a constant graph, 0 gradient. And the quantity of energy used here is 1675. I've taken account of kilo. So 1675 kilojoules. Then from there, another amount, certain amount of energy is also used. But this energy used, okay, raises the temperature from 0 to 100. So from 0 to 100, the temperature was raised. So this will give us a sharp slope because it's about sensible heat. And what's the quantity of energy used? This is what we use. But the total energy used is cumulative. So we'll add this to the first energy. To the first energy used. So 1675 plus 2100. And this is giving us 3775. So Q2 would be 3775, meaning this energy, which raised the temperature from 0 to 100, is added to it. Okay. Then at 100 degrees Celsius, okay, a change of state also came in. And the energy used in changing states, okay, is 111,555. So this will also add up to this. So 3775 plus 11,555 and 15,330. So Q3 will be 15,330. Okay. So this is actually a change of state. So this is how the heating curve of the question I gave earlier will look like. We are plotting temperature against the total energy here. So when you look at the last stage, you get the total energy that is used in changing states from 0 degrees Celsius to 100 degrees Celsius steam. So this is the nitty-gritties of heating. This one in particular is a heating curve. Things to denote whenever you see a gradient, then the gradient denotes sensible heat. So we have sensible heat here. On a heating and cooling curve, 0 gradient means latent heat. Latent heat over here. So we have latent heat over here, and then another latent heat here. Okay. Over here we have ice plus liquid in existence, because change of state starts at 0, and by the time it ends, everything has turned to liquid. So over here, you certainly have ice plus liquid in equilibrium. What do you think we will have along this path where we have sensible heat? What will be the state of the substance here from 0 to 100? What will be the state? Anybody to share the state with us? What do you think will be the state from 0 to 100? Oh, no response from you. What do you think will be the state from 0 to 100? Mamiya, from 0 degrees to 100 degrees Celsius.
I think it will still be ice.
Mamiya, look at it very well. You see, this is 0
To
degrees.
be liquid. Liquid.
It's liquid. So in between, from 0 to 100, because everything has turned to liquid, this is complete liquid. Then what is the state of matter at this level? At 100, what do you think will be the state of the substance? What do you think will be the state from at 0 degrees, 100 degrees Celsius? Anybody? Julian?
Yes, sir.
What is the state at 100 degrees Celsius?
So steam.
Julian
Okay,
is
no,
not.
sir. Just liquid.
Look at it again. Let's start. Let's start the whole show. At 0 degrees Celsius, 0 degrees is the melting point of ice. That is, over here, ice begins to melt. So in between we have both ice plus liquid. By the time we get to this point, this is the point where every ice has turned to liquid, and its temperature is being raised from 0 to 100. That is why from this point to this point we have liquid, but in between it is ice plus liquid in existence. Then when it is heated to 100 degrees Celsius is the boiling point of water. Okay, that is the stage where liquid turns to vapor. So what do you think will be the state of the matter in between? Julian again.
So please, liquid plus gas or something.
Exactly. So in between it is liquid plus vapor or gaseous. Okay. So these are the things we can deduce from a cooling or heating curve. Any question? Any question? Now, I want you to include, you see, I gave you from -5 degrees Celsius to -5 degrees Celsius ice to 100 degrees Celsius steam. Plot the heating curve for me. Use this as a guide and then plot the heating curve. When you finish, take a shot and send it to me. From -5 degrees Celsius. So you have plot a graph of temperature on the vertical, energy, heat energy on the horizontal. Okay. Then when you finish, take a shot and then send it to me. Whilst I look for other questions to try with you under this. We've done heating, so I'm looking. I wasn't recording all the while. Hey, Safu is gone. Okay, Leslie, let's hear from you. What is the melting point of the substance? Leslie. Hey, are you people there or you just don't want to talk? Priscilla, go ahead.
Say it's 40 degrees.
Arefa, what do you also think?
I was about to say that for
Yes, it's 40 degrees. Okay, because you see, solid, we have complete solid at the energy 110 to 160. So from that stage, it will be changing state from solid to liquid. So it starts at 110 to 90 or from 90 to 110. So the melting point must be 40 degrees Celsius. All right. Okay, then question 87. The specific heat of the substance. What is the specific heat capacity of the substance in the gaseous phase? The specific heat capacity of the substance in the gaseous phase. Calculate that for me. When you are ready, you share with us. The specific heat capacity of the substance in the gaseous phase. '87. The specific heat capacity of the substance in the gaseous phase. The heat of vaporization of the substance is, please, here is specifically the specific latent heat of vaporization. Latent, specific latent heat. Of vaporization. Okay. Yes. Who is true with question 87? If you are true with question 87, kindly share with us. Julian, what have you had for question 87? The specific heat capacity in the gaseous phase. Julian, are you there?
Yes, sir.
What have you had for 87? Were you able to solve it?
No, sir.
Okay, Mamiya, were you able to solve it?
I think the answer is 40.
40. 87. Okay, Elizabeth.
Since I had 30.
Calvin, what did you also get? All right, let's see. So the specific heat capacity in the gaseous phase. So gaseous phase. All right. So look at from 120 to 160. Okay, it's about sensible heat. Okay, and once sensible heat is the heat responsible for change in temperature. So we can determine specific latent heat of vaporization at that point. And how do we calculate it? Q is equal to MC delta T. What is Q? Q is a quantity of heat energy responsible for raising the temperature from 120 to, okay, this is a dropping the temperature from 160 to 120. So the total energy used there is 30 kilojoules. So 30 is equal to the mass of the substance is 1 kilogram. 1 kilogram times C, which we are looking for. And then the change in temperature is 160 minus 120. Okay, so 160 minus 120, which is 40 degrees Celsius. 40 degrees Celsius. Therefore, C is equal to 30 divided by 40. So what is 3 on 4?
0.75.
0. Hello, 0.
75.
So 0.75, okay, joules per kilogram per Kelvin. So that's the specific heat capacity of the substance in the liquid, or sorry, in the gaseous phase. The answer, or the option 1. Mamiya, Elizabeth, Julian.
You said that, please, I thought we were finding the specific heat of vaporization of the
That-
substance.
The question is saying
I
that 87, the specific heat capacity of the substance in the gaseous phase.
Okay, thank
Julian, are you okay?
Yes, sir.
Priscilla, are you okay? And Mamiya?
Yes, sir.
Yes, please.
Then the next question, 88. The specific latent heat of vaporization of the substance is, what is the specific latent heat of vaporization of the substance? I want you to try it. Don't forget, latent heat of vaporization, amount of heat energy responsible for change of state from liquid to vapor. So what is the specific latent heat of vaporization? So QV is equal to M times LV. and they are looking for this. I want to see how you can think through. Eva, are you there? Eva. Eva is gone. Michelle. Michelle. Class, when I call you for an answer, I'm not expecting you to give me a correct answer. I just want to know how you think about the question. If you are not getting it, after I'm here to guide you. So I just want to seek your opinion. Okay. So I'm actually disappointed in you not responding, wanting to be quiet. I just want to know how you think so that I can, realign your thinking. That's all. I can't teach you by, saying everything all the time. We must be interacting. The reason for which I call you to. So just tell me what you think and we move on. If you haven't solved it, those of you who were telling me that they haven't solved it, there's no way I'm going to beat you for not solving. Okay, so who can share with us what he or she thinks? Elizabeth.
So it has 120 kilojoules per kilogram.
120.
Yes, please.
Is your answer in the options?
Yes, please.
And then maybe you are correct. Let's see. 88. The, the specific latent heat of vaporization. So we go to the graph. Look at where we have complete, where everything changed to vapor. Okay. Specific latent heat of vaporization. So from liquid at 70 kilojoules, by the time we get to 30 kilojoules, everything has turned to gaseous state or vapor. So if we are calculating for the energy, it must be 70 minus 30. 70 minus 30, which is 40 kilojoules, is equal to, the mass is 1. The mass is 1 times LV. Therefore, LV is equal to 40 divided by 1. So 40 joule per kilogram. Who else had 40 joule per kilogram? None of you. Okay, let's go through the question. 88 is about the specific heat of vaporization. The foreign books call it as heat of vaporization for short. We are calling it specific, because about 1 kilogram mass, specific latent heat of vaporization. And this is the amount of heat energy that is required to change, okay, 1 kilogram mass, okay, from liquid to vapor. Now, on the graph, where do we look at? We are plotting temperature against total energy. Where do we identify the energy used? The energy used is the horizontal. Now, when you look at solid, okay, then change of state, please, let's go through the graph from solid. Then change of state from solid to liquid begins. So wherever you see a zero gradient line, no slope, it means change of state is happening there. So from 110 to 90, or from 90 to 100, we have change of state. So the quantity of heat energy used for this change of state from solid to liquid, or from liquid to solid, will be 110 minus 90, and that will be 20. Then from 90 kilojoules to 70, we have complete liquid. Here, we are only raising the temperature of the liquid from 40 to 120. Okay, so at 120, we have complete liquid, and then the change of state from liquid to gas will start. Okay, so the quantity of energy used to change liquid to gaseous will be 70 minus 30. 70 minus 30, which I've recorded here. The quantity of heat energy used to change state from liquid to gaseous, or vapor, 70 minus 30. And this is equal to the mass of the substance, which is 1 kilogram times specific latent heat of vaporization, LV. Therefore, that is the specific latent heat of vaporization. Elizabeth, are you okay? Elizabeth, are you fine? Mommy,
Yes, please.
Julian,
Please, I'm fine.
Yes, sir. Okay.
89. 89. What is the physical state of the substance at a temperature of 120 degrees Celsius? What is the physical state of the substance at a temperature of 120 degrees Celsius? So go and look at the graph. At a temperature of 120 degrees Celsius, what is the physical state of the substance? Yes, Priscilla.
Gas and liquid.
So we have liquid only, solid only, gas and liquid only, and 4 solid, liquid and solid only. Julian, what do you also think? What is the physical state? Priscilla has given us what she thinks. Julian, what do you think?
So please.
At a temperature of 120 degrees Celsius. Hey, Julian. Are you there?
Yes, sir.
What's the state?
So please. Gas.
Okay. Mami, what do you also think? At a temperature of 120 degrees Celsius, what's the physical state?
He says, sorry, I wrote up in gas and liquid. Sorry.
You were not looking at the graph. You were not looking at the graph. So it's gas and
Should
liquid.
I still answer? Okay.
It's gas and liquid. Okay. Whenever you have zero gradient at that constant temperature, okay, you have that mixed state of the substance there. Then 89. Okay, 90. 90. Compared with the specific heat of the substance in the liquid phase, the specific heat capacity of the substance in the solid phase, will it be less, greater, or the same? Listen to the question again. Compared with the specific heat capacity of the substance in the liquid phase, the specific heat capacity of the substance in the solid phase or state will it be less, will it be greater, or the same? Start work. So you are comparing the specific heat capacity of the substance in the liquid phase and then the solid phase. Okay, so the comparison is actually to the specific heat in the solid state. Will the specific heat capacity in the solid state be greater than the liquid phase, be less than, or be the same? Work it out and then I'll get back to you. I've solved, I think, one with you. I think this is the specific heat capacity in the gaseous state. So work out the specific heat capacity of the substance in a liquid state and then determine that in the solid state and compare the liquid state, C in the liquid state to C in the solid state. I'll get back to you. Well, I look at another question. It isn't difficult, but you just must be involved in what we are doing, share ideas, ask questions, and you'll be fine. So today, honestly, I'm disappointed with your contributions in class. Totally. Because I see this thing to be very easy, but the way you are not responding to me, me really hope. All right, so the last question, this last question, which is question 91, I'll throw it at Leslie. Today is here and she's not talking. Eva will not talk to me. Angel, there are your trotro angles. Angel, you are drawing angles. Okay, listen to the last question. As heat is added to a solid at a temperature below its melting point, listen, as heat is added to a solid at a temperature below its melting point, its average molecular kinetic energy, will it decrease, increase, and or remains the same as heat is added to a substance at a temperature below its melting point? Its average molecular kinetic energy, will it decrease, increase, or remain the same? Michelle?
So please, I think it would increase.
Any reason?
Because adding heat increases the temperature, which in turn increases the average molecular kinetic energy.
Okay, adding heat outside, outside its melting or boiling point. Because when we are there, when we get to melting or boiling point, and you add heat, it will not change the temperature, and so its kinetic energy will not change. So here, be specific. That's why the question seems to be clear that as heat is added to a solid at a temperature below its melting point, its average molecular kinetic energy certainly would increase. Okay, when we are extracting heat out of it, then its average molecular kinetic energy will decrease. All right, so that's just it. That's it. Okay, not difficult at all. Not difficult. Class, I've sent you another new set of questions. And this time around, Julian, are you there? I want you to be very, very attentive.
Okay.
Listen to the question. It's a cooling curve for 10 kilogram of a substance as it cools from vapor at 160 degrees Celsius to a solid at 20 degrees Celsius. So it's a cooling curve for 10 kilogram of a substance as it cools from vapor at 160 degrees Celsius to a solid at 20 degrees Celsius. Then energy is removed from the sample at a rate of 2 kilojoules per minute. Energy is removed from the substance at a rate of 2 kilojoules per minute, meaning that every minute 2 kilojoules of energy is removed from the substance. So when you look at the graph, it's a graph of temperature against time. Once for every minute, 2 kilojoules of energy is removed, meaning if it's 2 minutes, 4, 6 minutes, so you must understand. Okay, now the main question. Question 112. The boiling point of the substance is 113, the heat of vaporization. This is latent, specific latent. Okay. So when you see heat of vaporization, it refers to specific latent heat of vaporization. Heat of fusion is specific latent heat of fusion. So you have to determine the specific latent heat of vaporization of the substance. Then 114, during the liquid phase, the specific heat of the specific heat capacity. Okay, when you see specific heat, it refers to specific heat capacity of the substance S during the liquid phase. Then 115, while the substance is cooling during the liquid phase, the average kinetic energy of the molecules of the substance I decreases, increases, and remains the same. And then 116, compared with the specific heat capacity of the vapor phase of the substance, the specific heat capacity of the liquid phase, will it be less, greater, blah, blah, blah. Start work. Do it right away. Collaborate and do it. When you finish, send your answers to me. Please, I'll mark this. I've realized when I give you assignment, only a few of you make time to do it. So we are using the time left, about 10 minutes to do this. Start work. When you finish, take a shot and send it to me. LV is equal to QV over mass. So what is QV? QV as 2 from 2 to 9. So the time is 7 minutes. So if 2 kilojoules, okay, is removed per every minute, then Q would be 7 times 2, which is 14, divided by 10. So we have 14 on 10, and this will be equal to 1.4 joules, okay, joules per kilogram. But it will, of course, be kilo. So the specific latent heat of vaporization of the substance would be 1. Where is the question? Yes. 1.4, so D. Then 114. During the liquid phase, the specific heat capacity of the substance is during the liquid phase. So the quantity, the specific heat capacity C is Q over M delta T. What is Q? Q is 17 minus 9. 17 minus 9. And what is 17 minus 9? 8. So 8 minutes, 8 times 2. 8 times 2. 8 times 2 divided by 10 times, what is the change in temperature? The change in temperature is this is 120 minus 70. So 50.
50.
So we have 16 on 500. And what is 15 divided by 500?
0.032.
0.032 joule per kilogram per degree Celsius. So the right answer is actually the third option. Fine, it's kilojoules. So the third option. Then 115. 115. While the substance is cooling during the liquid phase, the average kinetic energy of the molecules of the substance, will it decrease, increase, or remain the same? While the substance is cooling during the liquid phase, the average kinetic energy of the molecule, will it increase, decrease, or remain the same? Yes. Any contribution while the substance cools, its average kinetic energy, will it increase, decrease, or remain the same? Okay, so the right, it will decrease.
Decrease.
It will decrease.
Decrease.
Oh, yes. Then 116. Compared with the specific heat of the vapor phase of the substance, the specific heat of the liquid phase is, so we have the specific heat of the liquid phase. This is here. So we must determine the specific heat during the vapor to make our conclusion or to draw it. So what is the specific heat capacity during the liquid phase? Q is 2. So 2. So it means 4 kilojoules divided by the mass is 10 times change in temperature. We have 160 minus 120, and this is 40. So 0.01 kilojoules per kilogram per degree Celsius. So when you compare, it means the specific heat capacity of the liquid phase is less. It's less than the, oh, it's greater, it's greater. This is, that's you. This is 0.01, and this is greater than this. So the specific heat capacity of the liquid phase is less than the specific capacity of the vapor, this is gaseous. Sorry, this is vapor. And then this is of liquid, C of liquid. So in comparison, you realize that the specific heat capacity of the gaseous phase, okay, is less than the specific heat capacity of the liquid state, or the specific heat capacity in the liquid state is greater than the specific heat capacity in the gaseous or vapor states. So the emphasis is compared with the specific heat capacity of the vapor phase of the substance, the specific heat capacity of the liquid phase is greater. So the answer is greater. Let me see by hands, those of you who scored everything. If you scored everything, let me see your hand and clap for you. Hey, no one. How many questions? 1, 2, 3, 4, 5. Oh, Julian, you couldn't score all. Mommy, Elizabeth. Okay, 4 out of 5. 4 out of 5. Michelle, Priscilla, if we're okay, that's good to know. 3 out of 5. 3 out of 5. Okay. All right. All right. Hey, so Leslie, you are here. Leslie, you are not annoying. 2 out of 5. 2 out of 5. No one. Okay. Hey, Kweku Angel. Okay. Okay. So please, yes, I'm sure you have identified your mistakes. Have you?
Yes, please.
Okay. So tomorrow we start a thermal expansion in solids and liquids. Thermal expansion in solids and liquids, where we'll be looking at linear expansivity, area expansion, volume expansion. Then we look at anomalous expansion of water. Next week, I'm hoping we'll start thermometry. Okay, so once you have heat, you have thermometry, calorimetry, you should be smiling to the bank. So this is where I draw the curtains on today's meeting. Thanks for your, but in fact, I have not been happy with you when it comes to contribution. Please, I always tell you that I'm not interested in your correct answers. I want to know, Michelle, your hand is up. Michelle, go ahead.
I wanted to ask if we are supposed to send our marked version, so it's okay.
Oh, you can send it. You can send it. You can send it to me. Because I was updating on the platform. Please send your work so that I update your name on the platform. Okay. So please, when I call for your views, even if you have no idea, tell me, and I won't hold your neck. Okay. But to be quiet, behave as if you're not around, sometimes it's very, very hurting. It's very, very hurting. I beg you. We are family. Don't do that. It will not help you. So we'll continue tomorrow. Take care of yourselves and bye-bye.